All right, I found this on AliExpress and I had to have one. It is, well, it says it is a power, it says 2 watts, 33 dBm, frequency 1 to 930 megahertz, version 1.1C. That's interesting. RF in, RF out, it's an amplifier. And so it has a particular gain, and it can go up to 2 watts. And it's a 2-stage. It's got stage 1, stage 2. And here's some DC biasing things to make these guys happy. Amplifiers need to be DC biased. I've added these loops. These loops weren't original. Added these 2 loops so I can connect ground and plus 12. 12 volts is what it needs. And it comes on a heatsink. So yes, indeed, it can do 2 watts because it's got a heatsink on the back. That's pretty cool. So I think it was like $7 or something. It was like super cheap. Like, okay, I'll get one of those. I want to do a particular measurement, and I think that'll be fun. And frequency range is good. So first of all, let's take a look at the schematic of this thing. Well, before we get to the schematic, let's just kind of take a look at how it's constructed. There's obviously some coplanar waveguide stuff going on here, so it comes straight through. The input is capacitively coupled, the output is capacitively coupled, the 2 stages are capacitively coupled, and then each of these devices are connected to this big copper ground plane. So this is connected to a ground pour, this is connected to a ground pour. This one has a bunch of stitched vias, which is nice. And so they get stitched to the other side. This one has some little stitching on it too. And then the bottom side is probably all copper, and it connects to the PC board. So the power comes in here, the plus 12 comes in here. There's a inductor to a bias, there's a bias T network for the last amplifier. And then there is a 5-volt regulator. So the 12 comes in, gets regulated into 5, and then the front end is biased at 5 volts, the back end is biased at 12 volts. And there's actually some other biasing in there as well we'll take a look at. So yeah, there you go. Let's take a look at the schematic. All right, so the input, all of the capacitors are 0.1 microfarads. They're all 100 nanofarad capacitors, so they just used everything everywhere. So it's capacitively coupled in, goes into an SBB2089Z. Yeah, that is the first amplifier. The second amplifier, I'm not quite sure what it is. It's got a strange marking on it, KB2X3. So if anybody knows what a KB2X3. If anybody knows what that is, comment below. Otherwise, it's just a mystery amplifier. All right. This one, let's look at this first. Well, see here. We'll talk about the DC biasing. So the 12 comes in, gets filtered. There's an LED that turns on. It says you've got power applied. And then 12 volt comes this way, and 5 volts comes this way. So the 5 volt, the 12 volt comes in through an inductor, and I think there's a ferrite bead. There's a funny little part right there and right there that I can't quite identify. I think they're ferrite beads, so it goes through a ferrite bead. And on this one here, we go through a ferrite bead, 33 microhenries, 33 microhenries. All right. So that biases the back end of the amplifiers. This one at 5 volts, this one at 12 volts. But then it's got this extra thing in here that actually, it gets divided down. The 5 volts gets divided down into 1.6 volts. And that 1.6 volts is the thing that biases the front end of this thing. Now, a lot of amplifiers are self-biasing on the front end. They need power on the back end, but they're self-biasing on the input. All right? So, let's take a look at this part number. I have a data sheet for that. All right, it is a, I don't know, Corvo? Qorvo, never heard of them before. It is in an SO89 package. High performance Indian gallium phosphide, mimic amplifier using Darlington, active bias network. So it has like self-biasing, run directly from a 5-volt supply, which is what, remember, it has that, this is the first one, has the 5 volts on it. Yeah, 50 ohms, you know, you got the inputs and the outputs. It is a 20 dB gain, plus 24 dBm output, absolutely. The 1 dB compression power point is 20 dBm. And that's what we're going to talk about today, is what does it mean to have a 1 dB compression, okay? This is how you would lay it out, very nice. And this is how you would set it up. You would have a thing like that. So, okay. What kind of values do they have for LC? I'm interested in that. 1.2 microhenries. Okay, that's good. And CB, yeah, see, 8,000. So that's only 8 nanofarads. And they have 100 nanofarads in here. I don't think these, I don't think these are the right value. I think they should be lower than that. They should be, anyway, it doesn't matter. Yada, yada, yada. It does frequencies and stuff. Anyway, that's what that one is. The other one looks like it requires some more help on the front end. I think this part already has internals where it biases the front end correctly. Because remember, it's capacitively coupled in, so there's nothing on the input, so it needs to have some self-biasing. This one gets biased up to 1.6 volts. A lot of times you'll change this biasing, like in radios and stuff. You'll probably be familiar with this type of thing. You're setting some kind of quiescent current, blah, 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 blah. Anyway, these guys should be set up to do that. You just need to give them some voltage. All right, long-winded. All right, so let's hook this thing up and make it go. Now, I want to talk about a particular concept. I talked about that 1 dB compression point. Well, what does that mean? All right. All right, so let's take a look at this first graph here. This is power in and power out, all right? So you would imagine that if you input a certain amount of power, it's going to give you some amount of gain, right? So let's say you enter 1 watt, okay? And the output, let's say, is 2 watts. It has a gain of 2. So you have 1 watt in, and you'll get 2 watts out. So 0 would be down here. So you'd say, okay, I've got 1 watt, okay? And it's going to give me 2 watts output. But what if I have 2 watts? Is it going to be 4? Is it going to then be, you know, is it multiplying? It'll be linear. Whatever, if you change the thing linearly, each time you'll bump up. So if you give it a little bit more, it'll go up a little bit more. Get a little bit more, it'll go up a little bit more, right? And it'll follow a straight line until it just starts running out. It just can't do it anymore. It's trying really, really hard. It just can't do it anymore. And it'll start to droop off, right? It'll go more and more and more and more, and then it'll start to droop off, okay? And this droop off is when a perfect one would just keep going up and up and up, but obviously there's going to be some limit. And whenever this delta here, this difference between where it should be and where it is 1 dB, you say you have a 1 dB compression. It's 1 dB less than it should be. So you can plot it another way. You could plot it in versus out over in. So out over in will always be a fixed value. It'll be the slope. So this is your slope. So it should be a straight line that goes straight across. As long as it keeps going up and up and up, it'll be a flat line, and then it'll start to droop off. Okay. And this is known to be a power sweep. We're going to sweep power, and we're going to watch the output, and it should stay flat if everything's doing good. But as you get more and more and more, it's going to start to droop off. All right. So that's what we're going to measure today. All right, this is a vector network analyzer, but it's a generalized RF analyzer. And a lot of times you'll be looking at graphs that are frequency versus amplitude, all right? And we're going to be doing something different with this machine because it can do it. And that is when you go to the sweep menu, you can do a frequency sweep or you can do a power sweep. And we want to be doing a power sweep. It says power sweep is allowed only in CW mode. So we have to pick a frequency. We're not going to sweep frequency, we're going to sweep power. So we need to pick a frequency. So in frequency, we're going to say, let's do 500 megahertz. Okay, we will just use 500 megahertz. And now we can go back to sweep, power sweep, and now we can sweep power, okay? So we're going to put the device in the sweep as an S21, and we'll have input. So we'll connect the port 0 to the input, and then the output can go up to 2 watts. So we're going to need to have some type of attenuator. So I have a 30 dB 5 watt attenuator that we're going to put in the back end. So that will protect our instrument. It adds 30 dB of attenuation, but it's a 5 watt heatsink, so we can do that. Now we're good to go. All right, so what we're going to do is we are going to turn on frequency sweep. Power sweep. So power sweep. We'll go to power. We're going to do a sweep range. So we're going to sweep a range of powers. So it'll do like a 15 dB, 13, it'll do a 14 dB range, -1 to -14, or -11 to -24. You get to pick the range. So let's start out conservative. We'll sweep between -24 dBm and -11 dBm and see what we get. We should get a straight line. All right, so let's go to sweep. Now we go to power on. Power start is 11, power stop. Okay, so power start's going to be, -21 or 22, whatever it was. Yeah, the bottom is -22, and this will go up to, go between -22 and -11, okay? And all right, so let's apply some power. We'll apply some power to the amplifier here. Ground in +12, and there we go, we've got a line. All right, so here's our line at +10. So we have -22 going in, and it gets magnified up with gain, but then it gets fall down with the attenuator and stuff. It doesn't really matter. We don't really care where this thing is. All we care about is the line flat or is it drooping off, okay? So let's set the scale here, scale per division. Let's go to 1 dB per division, reference level. Let's see here, let's go up. Yeah, there it is. All right, and you can see that we have a little bit of droop here, right? So it's maybe half a dB. Let's see, let's go down, go take it to a line here. Yeah, it's about a half dB drop as we go from -22 to +22. Now, obviously, the amplifier is able to go up to 0 dBm input and give us 30 dB output. Okay, so we can go to the next range. Right now, we're going between -22 and -11. Let's turn that off. Let's go to the power sweep range. We'll go to -14 to -1. Okay, so we'll change the power stop power to 0 dBm. And okay, so it's going to sweep between -14 and -1 dBm. Okay, so let's turn that on. And you can see now we have this huge roll off, okay? And so we are getting this terrible roll off at the high end. We could set a marker here. We could look for, let's see here, let's just scale. Let's kind of move it up, oops, not scale, reference level. Let's move the reference level so it's kind of on a line right here. And we'll move our marker so it's down 1 dB. It's going to be down 1 dB about here, okay? So at -7 dBm, we are at a 1 dB compression point, okay? So yeah, so this amplifier is not great. It is not great. All right, so let's do something else. Let's do a let's turn the RF off. Let's reset the machine. We're going to now sweep frequencies. So this thing is good from 0 to whatever 1 gigahertz. So our frequencies we are going to set to start will be at 300 kilohertz, stop will be at 1 gigahertz. And you would say, hey, that amplifier is doing great, all right? And let's take a look at how much power we are inputting. We're inputting 0 dBm. And it's only telling you part of the story. It's saying you've got particular gain, but all right, we're going to do an S21 measurement on the device. I'm going to put in a through. We're going to keep the 30 dB pad in there, so we'll zero it out as well. You can see we really don't need to do that. Everything's right here at -30 just fine, okay? But we'll go ahead and do it. We'll say cal, response, measure cal. Now it's at 0 dBm. So we've called out the attenuator. So now, if anything is bigger, it's because of the gain of the amplifier. So now we're going to put the amplifier back in circuit. And oops. Come on. And we'll apply power. And our amplifier is giving us about 30, put the marker on here, it's giving us about 33 dB of gain. All right, but it might be completely saturated. We did that other measurement, so we have to make both measurements. This looks great. You'd think it was just fine, but we can sort of see that in this measurement as well if we're clever about it. Let me turn the markers off. And let me go to power level. It's at 0 dBm now. We know that kind of saturates things, right? So let's go to power level and let's start lowering that power level. Let's go down to -12 dBm, -16 dBm, -20 dBm. And we can see that it's not completely flat with frequency when it's not saturating, all right? All right, the last measure we'll make is thermal camera measurement, and we'll take a look at how hot things are getting on here. So let me zoom you in on the camera, and you can see that the first amplifier is not getting hot at all. It's that second one that's getting hot. It's running here around 66C. And then the heat sink is running really, really hot at around plus 55 degrees C. So yeah, there you go. So things are within tolerance here. We can move it up to 0 dBm, and it should get hot, because now we're probably going to do the full 2 watts. Even if it compresses. A lot of times if you're doing FM modulation, doesn't matter if it's compressing or not. So, yeah. We're going to 69C. Over here we're getting 55. So that one's still saying about the same. This guy here is getting toasty. Let me zoom in here. I love this focusable camera. I can come here and focus right on that little guy. Yeah, he's 73C now. He's getting toasty. 73C is awfully hot. And this one's still at 5. Okay. So yeah, there you go. You can look at the PC board staying nice and cool. How's this little guy doing? He's running at about 48C. So compared to that one, he's cool. But yeah, let's focus again here, going on the out. Oh, there we go. Fun for the day. Buy some little RF modules from AliExpress. Don't expect much for them, but they're really good to practice your measurements and stuff on.